Right. Welcome to DSP CE 3007. Today is the 4th of February 2021. We are now in week 4 of SEM 2 2021. Today we will do this lecture, the part 4 of Z transform. This lecture was not recorded in the past. In the previous lecture, we mentioned that we will not test you. It's not that we are going to test you for these exams, but having a good understanding of how to interpret the Z transform would help you in your tutorial and exam questions. So today we would use this 40 minutes to go through this lecture, and then I will post it up along the lectures of what we have previously. Okay, so today we'll go to the interpretation of Z transform. There are three relationships that we can interpret the Z transform. The first relationship, in the last courses, we actually compare Z transform with DTFT. DTFT is discrete time Fourier transform. But since we haven't done DTFT, I would put relationship A last in today's lecture. I will talk about first, how to interpret Z transform as a sequence of numbers, because basically, for example, if I say h of n equals to 0, 1, 2, 5, 6, 0, 0, and so on, which is a sequence of number, and maybe this guy is h of n, this is a sequence of numbers. And by now you know that we can perform Z transform of h of n to become h of z. And then h of z is nothing but 1 z0 plus 2z minus 1 plus 5z minus 2 plus 6z minus 3 plus 0z minus 4, and so on. And you realize that this is a sequence of numbers, and this is a polynomial with variable z. So that's the second interpretation, and we'll actually begin with this interpretation first. And once you have understood this, then we can interpret the last interesting interpretation, which will actually bring us to DTFT. So let's go. We'll first skip to the DTFT first, and we'll go directly first to the interpretation of sequence to polynomial. Let's repeat the definition of Z transform. Given a Z transform, we take input is a sequence, and this sequence must be a discrete time because n is integer. N belongs to integer, so integers means you can have 0, 1, 2, 3, all the way to infinity, as well as minus 1, minus 2, all the way to infinity. The value of xn belongs to the real. That means the value itself can be a real number. What does Z transform do? Z transform converts a sequence of numbers to a polynomial. And how does it do it? It takes your sequence indexed by n, any of these index from minus infinity to infinity, and simply multiply by z to the power of minus n. And if you think of it just an algebra, then it does nothing but, for example, in this very simple example of 1, 2, 3, and I should, in my lecture notes, put a little arrow here to tell you n equals to 0 here. Now, when n equals to 0 here, then you look at this equation, and then we expand this equation into all its individual components. Then what we do is we have hn, z minus n, and since everything else after 0, 1, 2, everything else is 0, there's nothing to do for the sequence of, so we actually ignore this. What about on the left hand side, minus 1, n equals to minus 1, n equals to minus 2, they are also 0. And so on this side, 1z plus 1, actually 0z plus 1, 0z plus 2, all these are also 0. So there's nothing to do also, and we circle this and we kill it off. So from the Z transform perspective, if you now look at this in as a linear algebra or as an algebra problem, we are converting a sequence to a polynomial. Remember, a polynomial is simply, some constant multiplied by some variable. And then you'll be thinking, what is the variable? And the variable, as you now know, is Z. And what is Z? Z is complex number. And then which number? Any complex number that you can choose. You can choose Z equals to 0 plus J0. You can choose any A plus JB. For A belongs to the real, B belongs to the real. Okay, so when he says any real number, it's exactly what it means. The problem, of course, then is how to interpret this. But if we stop here, if we actually stop the interpretation, and we simply say this is HZ, and this is the sequence, then there's one interpretation as well. The interpretation is this, which is very interesting. On the left-hand side, you have h of n, which is just a sequence of numbers. On the right-hand side, you have a polynomial with the same number. But then it says, but you have z. And these z's are indexed by 0, -1, -3. Oops, I think this is wrong. This is 2, huh? Okay, guys? This is 2. -1, -2. Okay, please change this. Now, what does the z with the index tells us? The index tells us the position in time, because this is n equals to 0, this is n equals to 1, this is n equals to 2. So, although the index is still there, the negative sign is just introduced. So if we understand this, then we can actually get back from this sequence or this polynomial back to this sequence. Now, what is the interpretation then? Actually, you have done nothing but just convert a sequence of numbers to a polynomial. All the coefficients are there. Nothing has been changed. Therefore, you can actually get it back, and therefore this is a lossless transformation. You have transformed from something to another thing, and you can get it back. Okay, so that's the nice interpretation. And in fact, when we do Z transform for finite sequences, it's very simple. Okay, now, another interpretation. This guy, such kind of equation, h of z. I mean, you guys have seen y equals to y of x, so not y of x, sorry, f of x. F of x equals to 1 plus, some c1 x plus c2 x squared plus c3 x cubed plus. Then if we replace x by z, 1 plus c1 z plus c2 z squared plus c3 z cubed. Oh, okay. So if you now look at this pattern, then you say that, oh, okay, h of z is what we also known as a power series. And in fact, it's a very special power series. It is a Maclaurin series. Okay, so you have done this in A level, and you have seen that the Maclaurin series basically represents a function as some power of some variable. Okay. Always remember that our variable z is a complex number. And in your typical A-level problem, x is the real number. Okay, that's the only real difference between fx and h of z. So in math, if you go to something called complex analysis, this is where we are now. We're doing complex analysis. All right, but anyway, we are still in, we although it's a complex analysis, it's still a power series. And it's a very special power series called Maclaurin series. And the variable z is a complex number. Okay, what else? Now, then we come to this guy, okay? Our problem, h of n equals to 1, 2, 3. And I should do this. And I should say this. And I say now, perform Z transform. And I get h of z equals to 1z0 plus 2z minus 1 plus 3z minus 2 plus, and actually if you really want to, you can do this, but nobody does this anyway, right? So this guy goes away. Now, how do I write this equation? Then he says, okay, this equation, I can write it in this form. 1 times z0 is 1. 2z minus 1 is plus 2 over z. Plus 3 over z squared. Okay, so this is how I want to write it now. And then this is still h of z. Okay, now I say z is a complex number. Let us now find a complex number. So remember that when you draw a complex number, I first draw the real line. I find where is my 0, where's my 1, where's my 2 along the real line. I find where's my negative 1, negative 2, and so on, and it goes to infinity. So this is my real line. I should write real line nicely. Real line. What about my imaginary line, guys? So along here, I will draw this, the imaginary line, which is here will be j, 2j, and here will be minus j, minus 2j, and so on. This is the imaginary line. Now, if I give you z belongs to the complex number, is for example some a plus jb, then this point would be 2 plus 1j. So everybody knows this. All right. Now with that, we are going to begin to sketch this function. So how do we sketch this function? Well, this is my real line. This is my 0, 1, 2. Minus 1, minus 2. This is my imaginary line. Actually, it's this line, okay, guys? I should use a different color. Now I'm going to color it using, wait, so this is my imaginary line. Where's my real line? Oops. Actually, my real line, I made a mistake, guys. My real line is along this line, the blue line. Okay? And this point here is 0 for real, 0 for imaginary. What about this point? Which is this point, exactly where I'm drawing now, is 1 for real, and imaginary is plus j0. What about this point? This point is 0 for real, minus j, 1j. What about this point? This point is 0 for real, plus 1j. And what about this point? This point is minus 1 plus j0. Okay, so now you can see where all the points are in the complex plane. We call this thing the complex plane. Okay, and now I can choose any point I want. And then if I choose any point I want, what do? I plug in a z. For example, I'm going to plug in the easiest value I can plug in is minus 1 plus j0. Z equals to minus 1 plus j0. This is this point here. Because I can look here, this is minus 1 in the real and 0 in the imaginary. So what do? I plug this here into this equation. So h z equals to minus 1 plus j0. And what do? I plug this value into here, which is 1 plus 2 of minus 1 plus j0 plus 3 of minus 1 plus j0 square. And then I get 1 minus 2, and then minus 1 square is 1 plus 3. And the answer is 2. Okay, and how do I know if I'm getting it right? Okay, I'm going to use MATLAB and show you. Okay, MATLAB. So clear, oops. So z equals to minus 1 plus j times 0. So that's my initialization of z. And then my hz, okay, I just equals to 1 plus 2 divided by z plus 3 divided by z times z. And the answer is 2. Yay! Of course, if you are really, then you say z. What about z equals to 1? You change the value, plus j0. Okay, you will go and figure it out. What about j? Oh, I get a complex number. But this is to be expected. Okay, guys? You punch a complex number into an equation, typically out comes a complex number. Now, then you'll be thinking to yourself, I am putting a complex number, and that's fine because I can put any complex number in my green where I'm shading the green. And in fact, it goes from minus infinity to infinity. Any values. Out comes a complex number. A complex numbers have two terms, real and imaginary. And how can I plot 2D? This is 2D, right? I need another 2D, which I cannot see. So what do people do instead is they do not plot the 2D complex input to the 2D output. They only plot the magnitude and the phase. So what do I mean? Means that instead of this, instead of getting h of z, I type in, let me get absolute of h of z. Absolute of h of z is what? Absolute of h of z is the absolute value, which is 2 square plus 2 square root. Okay, so square root of 8, I guess, is, yeah. So what about angle? Angle of a complex number in radian. So the input is j. Where is my j? Let's find our j here. This is 1j. This point, if you look up, this value here will be the value that I have calculated. But typically, this guy is in a log scale. So please be very careful when you are observing this. Okay, this is in log scale, and therefore sometimes you say, hey, why is not my number? Or you just times log of that number times 10 or 20, and you'll get the value. We'll postpone the discussion why we are doing log scale later on. Okay, now, what else I want to do? Maybe I should show you this value here. Notice that this surface goes down to negative infinity. Why? Why negative infinity? The roots of 1, 2, 3 is this. Okay, so I'm going to do z equals to minus 1 plus 1 point. In fact, this is minus 1, okay, minus 1 point minus j times 1.414. So it's, wow, very, very small number. In fact, if I do square root of 2, it will be infinity. So square root is, so it's very, very small number. You can think of this as 0. Log of 0 is minus infinity. And hence, at this point, it goes to minus infinity. Okay, so now, guys, I cannot hear you at all. So can you tell me, do you know how to plot this surface now? It is nothing but putting this equation and populating all possible z's, getting a complex number, taking the absolute value, log it 10 times 10, and you get this surface. And then you can plot the angle as well using the same equation. Okay, clear? Can someone tell me in the chat whether you have any questions so far? Please. Okay, so if you have no question, basically I have just went through Z transform from a sequence to a polynomial to plotting the surface of H of Z, and then you can read about this here. Okay? All right, and with that, now I can talk about the second interpretation, which is as an inner product. Now, this equation is the definition of Z transform. Nothing has changed. But in fact, this equation is a realization of this equation. Or in fact, this little arrow here, this bracket here, has an interpretation in something in linear algebra. And when we say, let's say we have x comma y, and when x, for example, is a vector 1, 2, 3, and y is another vector, maybe 2, minus 1, 3, for example, and then what is this doing? This is doing x bracket I, y bracket I equals to, let's say this is 1, this is 2, this is 3, 1, 2, 3. All the elements multiplying with each other. That's what it's doing. Okay? And therefore you're thinking to yourself, so what is this little thing that it's doing? Which is nothing but multiplying all the terms together. 1 times 2 plus 2 times minus 1 plus 3 times 3. The answer is 2 minus 2 plus 9. And the answer is 9. So this vector 1, 2, 3 inner product or dot product with 2 minus 1, 3 equals to 9. Now, have you seen this before, guys? Have you seen this operation called inner product? Can someone type for me in the chat box, please? Inner product is a dot product but with complex. Yeah. Okay. Yes. So it's a dot product. So let's see. Now, so in fact, right, one important learning is that once you know the name of the problem, inner product. Okay. So you go and read what's the inner product, what's the dot product. So it is something that is not so difficult later on. You'll see that, oh, we are writing a lot of this triangle thing, and this is the dot product, and then this is also what I've just shown you. Okay. But then you say, what has this got to do with this equation, right? In fact, this form, yeah, is saying the sequence of Hn is performing a dot product with a sequence of z minus n. Okay, and you'll be like thinking, what is Dr. Cheng talking about? All right, now let's try. Let us just play with Hn equals to 1, 2, 3, 4. That's the easiest, okay? The n equals to 0, and the rest of the numbers here, I should just so this sequence is, it looks like this: 1, 2, 3, 4, and all 0. Okay, so this is a real sequence of numbers, and this is h of n. This is 1, 2, 3, 4. All right, now because all these values are 0, therefore something multiplied by 0 is not interesting. So we are left with n equals to 0 to, so 0, 1, 2, 3. Whoops. Okay, so if I give you a finite sequence, the problem is relatively simple. Very complicated problem reduces to a fixed sequence. Okay, h of n, z minus n. Now, let's open it up, guys. I told you that this guy looks like this guy. So I'm going to do inner product of, what's this number? 1, 2, 3, 4. So far, okay? So this is still h of n. What about this guy? So once you have figured out this vector, then, okay, let's plug in. Okay, let's force fit in. Z to the power of minus 0, z to the power of minus 1, z minus 2, z minus 3. What is z? Then so again, what is z? Now, when that question comes, then you say, I will fix z to be any values that I want. So then, what is this? If you understand, this is a vector. So you say this is a vector, and it's a vector from z0, z minus 1, z minus 2, z minus 3. But how do we interpret? Okay, now let's turn our attention to our friend, the complex exponential. E is a complex number. Ej omega n is a complex number. The complex number Ej omega n has absolute value of 1 and angle of omega. That's why we draw the real line and the imaginary line, and we draw this circle of radius 1. Any of these xn will fall on this circle. Okay, and then this point is along the real is 1 plus j0. But the next time when I did n, he's going to be jumping here, to jumping here, jumping here, jumping here along the unit circle. Let's see.
Is simply e to the
okay, I can't hear him. Can you guys hear him?
Recursively, we're going to generate successive samples
of these tell me if you can hear
exponential. So let's start at x0.
Oh, I can't hear him.
It's straight
okay.
on the real
so our friend Vitaly now is telling us that if we start here, after n equals to from 0 to 1, it will jump by omega because we have this little omega here. Omega n. See, omega times 0 is 0, so it is this point. Omega times 1 is this point. Omega times 2 is this point. Omega times 3 is this point. Let's see.
That gives x1 by 2 omega is x2, etc. It will keep going x4, 5, 6, 7, and so on.
Now, if you reach this point, you realize that our friend just plotted for me x0 to x7. Let's come back here. What do I need? I need Z0 to Z3. Because what is Z? Z is, in his example, in Vitaly's example, Z is 1 ej omega. This is, the first one is 0. Second one, 1 ej omega 1. Third one, 1 ej omega 2. Can you see now? But of course, I still haven't tell you. And the last one is 1 ej omega 3. But I haven't tell you what is omega yet. Well, omega is up to you, right? You decide which omega. Then, when you realize that, by generating different omega, you are spinning along this circle at different speed. Okay? And then, when you spin the circle at different speed, it is the frequency, the angular frequency of this guy. How fast is he spinning? And when you reach this point, then you have another interpretation. Your interpretation now is, let's say this is angular frequency. We are, and the answer is in this interpretation. We are comparing h of n, a vector, to phi z of different frequency. And then we are actually measuring the relationship of hn to phi z. And in fact, when you reach this, this is DTFT, especially because when z belongs to 1 ej omega n. Alright, so you can go and read this, and it is not simple, but it will provide you with a deep understanding of what is Hz interpreted from the inner product. Now, maybe I should continue this. Typically, for discrete time Fourier transform, Z is on unit circle, meaning we are only interested in Z that is belong to 1, the magnitude, ej omega, for omega equals to 0 to 2 pi. Where is 1 ej omega? It is where is 1 ej omega? It is this red. It is this red. What do you call it? The red. This red line. And if you project it down, it will be this circle. Z along this circle, when we bring it up, is this red line along this surface. Okay, and we're very interested in the values along this circle for h of z. So this h of z, this one is this one for and this surface. Now, okay, any questions, guys? You have to read it very, very carefully, and then when you do, then you will understand. Okay, but maybe I would now show you what different z means. Remember, I say that z can be anywhere along the complex plane. So this is the real z, this is the imaginary z, and I take different values along this point. And then I will now plot for you what is this plot. This plot is the values that you will get from plugging z into this guy. So basically it is a vector, and then this guy will be z minus 0, z minus 1, z minus 2. Okay, by putting in the value z and generating different powers of it, you will get a vector. And now I will show you this vector. This vector is here. So this, let's zoom in. this is n equals to 0. Next one, n equals to 1. Until n equals to 50. Now then you get different curves. Very interestingly, when you move up the omega, then what happens is we get a sine wave, and we go up along another omega. What do you think happened? The sine wave becomes faster. When we go up here at pi over 2, every step he's making is 90 degrees. Oh, okay, remember guys, this is omega equals to pi over 2. Every step I will make 90 degrees in a cosine or sine. So omega shows you the speed of the complex exponential, and here I'm just showing you the real part. Okay? And as I spin even faster, and I spin even faster, okay, and so on. All right. So this is the interpretation of C going from omega equals to 0 to pi. But then you say, but you can change another value. The value is here. At different C, I fix the omega. But now I can have the magnitude moving to 1, greater than 1 or less than 1. What's happening? Here is outside the unit circle, 1.2. Here is 1.1. Here is 1. Here is 0.9. And here is 0.8. And what's happening? They are all rotating at the same frequency. But some of them are dying faster. So this is very fast, it dies. This is slower. This is not dying at all. This is becoming fatter. And this is exploding even faster. So it has to deal with the magnitude of C. So after a while, you have to realize that now this is very complex already. So you have to read and then figure out, okay, with different values of C, what is, and then you say, what am I playing with? And you always come back to here. You're playing with this vector. By plugging in different value of C, I'm generating different things for you to see. And when you see different things, you realize that this guy is nothing but going to be inner product or dot product with Hn, and therefore now the problem is, what does it mean? Right? We're always generating a sequence, but what does the sequence do with our Hn? And that comes to our last part. What is an inner product? How to interpret an inner product. Okay, wait. Wilbert asked a question. How do you convert the inner product into the summation of Hn times complex conjugate? The definition of inner product is a vector. In this example, it's a vector multiplying by another vector. That's the inner product. Okay? And here, we are going to use the complex conjugate. Okay, let's not go there yet. The explanation you can find in this discussion here. Okay. But now let us interpret why are we doing inner product. And the answer is, in this example, let us have a vector B. And let's have a vector A. And I'm going to do B, A. And what do I get? And what does it do? It gives you, what's my number one? A dot B is here. It means it is actually, let me figure this out first. Here's the explanation. Good. A dot B is equals to B dot A. If this guy, the length is 1, then A dot B and B dot A is, so the length of A is 1. Then it is you are left with here, B cosine theta. What is B cosine theta? Then if you look at the equation here, B, this is theta, the angle between A and B, it is here. The dot product will reveal the length of B along the direction of A. That's the cool idea. The dot product will tell us how much of B is in A. Okay, so you read this, and then let's go back up again. Now, if you understand this term, how much of B is in A, then what am I asking you to do? I'm saying, how much of H is in this vector? By changing different omega, how much of H is in another vector? How much of H is in another vector? And now, we are like using the second guy as a ruler, measuring the contribution of H on the ruler. And this ruler is based on different frequency. Okay, and then we'll finally get H of C at all frequencies. And that's the interpretation we want you to do. Once you have this interpretation, then you can go back to the first DTFT. You'll realize that the first interpretation is the easiest. It is x of n with a sequence, and this sequence is depending only on omega. I am taking my input and measuring it against different sequence based on different omega. And with that, I will now measure xn at different, what is omega? Different omega is the digital frequency. Different frequency. Okay, and if you can reach this point, in fact, you say, if I just see the math is doing nothing but projecting xn at different frequencies. Finish. In DTFT, we will show you how to interpret xe j omega. Okay, with that, I think I'm done with this lecture. And this lecture is rather theoretical, very difficult, but it may help you to understand how to plot the H of C as well as DTFT understanding. Okay, so I'm going to pause here now, and I'm going to take questions. Right, so with that, we have just finished recording part 4 of interpreting the Z transform. I'll put up this video in the DSP, and then I think with that, we have the complete set of notes and video for the Z transform. Okay, with that, thank you. I'll see you all next week.